we as generations pass, better and better training occurs, and it is not back at what we learned and when we were BSc students. I think this is the tone in which Professor Mishra was mentioning before. So things should move in the forward direction, and it should not be static.
When we said that we are not teaching this, it was from our feeling of guilt that we can't do many things.
So I really like that statement. I completely agree. Okay, now we are ready to look at the general case for writing the Lagrange. We had discussed two examples. The first example was in which I had a block slide over another block which was moving, and the second one was a bead moving in a wire. The first example did not involve any explicit time dependence of the constraint, whereas the second one, there was an explicit time dependence of the constraint because the bead was going around. Now, we will keep all this in mind, and I will write down the general case. The basic thing, all this comes from the De-Long principle. Which I have already talked about. Definitely, I'm starting around 12, so I'll try to, I want to come up to points in special theory and creativity and stuff. You will have to be a little patient today.
There's a canteen person that
Now, the basic equation that we have is the virtual work due to a virtual displacement is given by this was V. This is essentially the virtual work done in the system, and we need not worry about constraint forces. That is the advantage of working. Now, the first important concept is degrees of freedom. We have already introduced all this. It is the number of independent variables required to specify the system. When I mean by independent, I should be able to vary a particular variable, keeping all the other variables fixed, and I should be able to vary that. And for each one of the variables, that is the state. The motion is described by the time dependence of these variables. Usually, these are some position vectors, some angles, and they are the kind of things that we deal with. We will refer to these as generalized coordinates. So, I will write down them as generalized coordinates. I am using Z nowadays because when I try to type something, it immediately objects if I don't write Z. This is n degrees of freedom. Now, we will consider a collection of m particles So in principle, I have to specify the position vectors of these m particles. So I have to specify R1 vector. But these things get automatically specified by my generalized coordinates q1 to qn, because I have said that these generalized coordinates specify for me the entire position vector of all of them. If you remember the example of the block, I had two particles there, one small m, another capital M. So it was a two-dimensional motion. So I would have had R small m and R capital M. But these are now four independent parameters, but they were completely fixed by xm because the big block only moved in the x direction, and then one more coordinate from the top of the block to here. So I needed q1 and q2 would correspond to my xm and d that I had assumed here, and r1, r2, rm would be the rest. That would be that example. In the next example, I just had actually 1 degree of freedom, that is q of t fixed everything x, y, z, t of the one. So now I will write it down as r vector as a function of q1 and in general function of t I. Let us take some simple examples of system. Suppose I have a rod moving on a two-dimensional plane. How many degrees of freedom would I have? A rod moving on a two-dimensional plane. I have to fix one point of the rod in the two dimension, so that will give me x, y coordinate of that. Then after that, I need to know the angle of the rod. So I have only one more parameter. So that would be 3. So let's write it down. Rod moving on a plane. Well, it will need not be horizontal, but I am just writing it. The degree, 3 degrees of freedom. Rod moving in 3 dimensions. The rod moving in 3 dimensions.
5.
Somebody say 5, somebody say 6. It's a good, very good answer, because now one can debate and ask why 5, why 6. So let's go. I take one of them here. Right. That is 3. Then what do you mean r theta and phi? I have already come here. The rod's length is of course fixed. So I can now theta and phi. So 5 degrees. The rigid body moving in 3 dimensions. 6 degrees of how many degrees of freedom? 6 degrees. To see this, the following is the situation. Let's consider this as the rigid body. Now, I can go fix this 3 degrees of freedom for this. I can treat this edge as a rod. So I need 2 angles associated with this. But still the rigid body is not fixed. I can rotate about this, and this direction of the rod nor the position of the rod has changed. So the body will be fixed only if I fix one more angle, the angle of this position of the rod. So that gives me 3 degrees of freedom. Another way of saying it is, let me attach an axis to the rigid body. So I have my set of axes x, y, z here, and the origin of this I need 3 coordinates. Then so I need one to fix, two to fix the z-axis because that's a rod, and one more angle about the z-axis to fix the sixth one. This is clear. So rigid body freedom. Incidentally, if you want to derive this, supposing we have an m particle system. So I have m particles. In principle, there should be 3m degrees of freedom. But what are the constraints? The constraints are each particle is the distance is fixed, angle is fixed, and so on. So you should be able to write a constraint equation and to be able to show that it is only 6 degrees of freedom. I was discussing this with Professor Ashok Kapoor of University of Hyderabad. He says this derivation is not simple. So he told me that there is a very recent paper, and the paper quotes a work of Einstein regarding this problem. And Einstein wrote this paper in his book called Essays in Science. I presume many of you must have seen this book. It's a very nice book. It has some very nice articles. If I get a chance, I will mention this. Essays in Science by Einstein. It's a very thin book. I have not yet had a chance to look into what I am going to say, but I certainly will. And then the proof is supposed to be given. A recent article about a year or so ago has pointed out a mistake in the proof of Einstein, and they have corrected it. Ultimately, of course, the answer has to be 6. So, why again, if there is a very interested student who is very interested, you can make him go through this, and he will enjoy seeing how these things come. Okay, so these are the examples that I have in mind. Ashok Kapoor has passed that paper to me, so if some of you are interested, I can certainly pass it on. Now, there are some words associated with these which I never remember properly. One, these are all given in joke and drama. I'll just mention it. If it is time independent, constraints. I'll just write them down. They go by the name where do these names come from? I don't know. This one. And if it is time dependent, that's called
some books are
pardon?
so in some books it is in a time independent of holonomy.
No, that will come. I'll come to that. If a particular constraint is valid for all times, okay, for all the time, that is a holonomic constraint. Have a constraint for an infinitesimal time, infinitesimal displacement, it is not necessary that you will be able to follow it for a finite displacement, for a finite time. Those kind of constraints in general are non-holonomic. I will not discuss non-holonomic constraints here. To discuss non-holonomic constraint in the context of Lagrange's equations require some more work, and it is not so simple. So I will just not discuss that. Pardon?
Einstein defines holonomic as inequality.
Yeah.
F of something equal to 0.
That's correct. So that will be that will be some. After all, I have n. So there must have been 3m minus n constraints in this, right? I am able to describe the system with n degrees of freedom. The total number to specify is 3m. So 3m minus n constraints. Correct?
3n minus n.
3m minus n constraints. This is the number of constraints I must have, so that I can describe the system by n constraints. If I have m degrees of freedom, there are
If you can write equation, you can write constraint as some equation.
yes, that's exactly right. That's what is meant when I mean by constraint value for all time. Supposing I have some constraint of R1, R2, Rn, right? These are constraints alpha, Rn, t. If I can write it in this form for all t, this will be a holonomic constraint. And this alpha will run from 3m minus t.
Note, in this definition, particle inside a sphere for all time. This definition will include that kind of constraint also.
No, it is not an inequality. That one is an inequality constraint.
Inside,
But that constraint I am not going to deal with.
No, I understand that. All that I am trying to say is that the definition that you have written does not imply a lack of inequality. It could also imply inequality. This definition. That's why I am saying.
No,
suppose
this
suppose
is
you put
equal
a
to 0. I have put it equal to 0.
suppose if
Yes, yes.
you put a constraint that particle is inside the box.
Right. That
That is
I am not going to deal with
No,
that.
but for all time, if it is going to be inside the box,
But
according to this definition,
what
it is also.
what I meant is it must be equal to. Okay. What you are saying is this doesn't yet imply that.
But it should not involve velocity. The constraint equation should not involve velocity.
But I have explicitly these are the nature of constraints that I will be dealing with. Okay.
So these are the equations of constraints.
These are the equations of constraints. Alpha is from typically non-holonomic constraints occur in rolling, and I will not be dealing with them.
So when there is some resistive forces appears, that's
Pardon?
non-holonomic.
Pardon? If there is a non-holonomic, we have to have a separate discussion. So right now I am not going to do that. Okay, that will take us away from what I am planning to do. Okay, so now let's look at the velocity of the ith particle is dRi by dt. This is equal to summation dRi by dt. A going from 1 to n dq by dt plus which I can replace this by 2k dot. This is my equation 1. As yesterday I had a very good suggestion saying that I should write equation numbers. Later on when I refer to them, it will be easier for them to refer. Okay. Now, from here I get, this is Ri dot, so I get dRi dot by d 2k dot is equal to dRi. Remember, this is a relation which we have verified explicitly for the example 1 and 2 yesterday when I had work. It just comes coming from here because this doesn't contain 2k dot as Professor Mishra mentioned, and this also doesn't contain 2k dot as this. So that's one relation that I have. Now we go to virtual displacement. This is one. So if people want me to number some equation which I might forget, please say so, I will do that. So that it becomes clear what I am referring to. So I have my delta Ri, which I will write it as dRi by d2k. course, I can use the Einstein summation convention. If since k is repeated, I can do that, but I have not. Now remember, this quantity here, in principle, can be functions of 2k's. So, even though delta 2k does not depend upon time, delta Ri can depend upon time. Okay? There is a difference between delta 2k are the ones which require to specify the configuration. But delta Ri are the position vectors of the various particles that I am talking. So, delta W for this is nothing but summation Fi Ri. I is the summation Now, I need not take the forces of constraints into account. That is, of course, the main part of the story. In this, I need not worry about the force of constraints. I will only take the external forces in the system. I'm just interchanging the sum of these two, and I write this as F1. And this quantity here I will call as generalized force. This is my equation 3. And Fk is the generalized force. Let me also keep that here. And that's my equation 4. This is the generalized force.
I summation is up to M.
What?
I summation is
Up to N.
Capital M, not N.
Oh.
And in 3 also.
Here M. So here this becomes. Here K is this is okay, and this is going to that. These are the generalized force. These forces that are there will have the dimension of force. But Q may not have the dimension of length. Q could be just some angle. So, this generalized force need not have the dimensions of the standard force. For example, if Q were an angle, this will be force times length. That will be the dimension of a torque. So, this could have a dimension of a torque. So, a generalized force need not have the standard dimensions of force. This is clear? Because Q need not always have the dimensions of a length. And this also, notice from this expression here, I can write down one more expression for f of k, which, let me write it down here. Yes. F of k. I can also write down. Just from this equation 3, I can write delta W by delta. This is my my equation 5, and that comes from 50.
So,
Yes.
see, that is what delta omega, the delta W is equal to summation of K is equal to 1 to N.
Which
Delta
one?
F,
We
yeah,
have equation 3.
From here if you are taking that, but
Yeah.
that is, there is a product.
No, I am differentiating this delta Wk, holding other k's fixed. So that is delta Wk by delta Q. Here, all other Q1 to Qk minus 1, Qk plus 1 to Qn is held fixed.
It is differentiation.
This differentiation,
What-
exactly. The only point is, these are using virtual displacement. So that's why I kept a delta and not a partial. Just to remind myself that that is the delta that I am using. Okay. Now, the next is I have to write down now the kinetic energy. E is given by summation m dr by dt dot drr dt. Now I going from 1 to m. What would this be a function of? This would be a function of Q1 to Qn, Qn dot, because I have differentiated it, Qn dot, and in principle the function is fine. So I write down dt by dqk is equal to half, half will go away, I differentiate this, so this will be I going from 1 to m, mi d r I by dt dot, this is ri dot, so I will write this as ri dot. But this is pi, so this is nothing but summation pi, I going from 1 to n dot d r I dot, and this I'm going to call my equation number 6. Now let me write down dt by dqk dot. That will be summation mi dri 1 by dt dot
So there is half.
Pardon?
dq by dq, there is half.
Where is half?
In second.
Second. This
First,
equation.
there is half.
So it will become double. There are two terms.
When I differentiate it, it is dri, dri. So it is dri dot square. So that 2 factor cancels. Okay. This is nothing but summation of So now I write ddt of dt by d2. This is equal to summation.
So it should be dot.
Yes?
Previously it should be dot. dri dot by dq dot.
Which one? Here? Next one, I have used equation 2. So I have dri dot by d2 radius is equal to dri by d2. Now I write down pi dot dri by d2k plus summation d2k. I'll just wait here for a minute. A small explanation. Is it alright? Now, this is my equation 7. One point, when I differentiated it, I took ddt of dri by d2. So I have interchanged my differentiation, and so that became dri by dt, and that became my ri dot. Now I subtract 6 from 7, so I get ddt. I'm now coming to the Lagrange's equation. Notice this term and this term cancels. So I get this is equal to summation of d5 But pi dot is all the forces acting on R, right? All the forces in the medium. But I know that here, when I am calculating this quantity, I need not take all the forces. The constraint forces give me 0. So I need here only to take external forces. And this is equal to, from equation, which equation? 4, this is nothing but this is the Lagrange's equation for a generalized force. For the case in which the external forces can be written as a gradient of a potential, for all those forces, if external forces I can be written as minus del times the potential V R1 to Rm then my W for this would be summation Fi dot integral, I'm writing W, integral with a minus sign, Fi dot dRi which is equal to minus I. Oh, I should write here del ith derivative for the ith one. It is on the ith particle. I should write down the derivative. So I should write down del I v r1 to rn dot dri integral. Now here I am going to write down this as dri by dqk delta qk. So I write it down as a sum over k going from 1 to n. Dot dri by dqk or delta.
So first then, you have taken minus of material, right?
Yeah, I have all that's the way potential is usually defined. Gradient, the minus.
Then this will become plus.
Minus overall.
Oh,
Right,
okay.
right, plus.
That's plus and yes. Thank you. So this is dTri dot dri by dqk. So this I can just sum I going from 1 to. This is m. And this is no. This is n, right? So this is k going from 1 to n integral dv by dqk. So delta W by dqk is nothing but minus dV by dt. But this is nothing but my generalized force F. And so if I write this equation number as 8 and I write this equation number as 9, I can combine 8 and 9 to write the Lagrange's equation in the standard form. So I get ddt dt by dq minus CL sub dt by dqk equal minus dv1. If I assume my potential does not depend upon q dots because I have assumed it to be functions only of r1 to rn, then I can take it to this side and rewrite this equation as ddt, the standard Lagrange's equation that we all write. Now, of course, we can apply this, and I have already given you several problems to apply this. And let me quickly summarize the main result. We have used the principle of D'Alembert, which says very clearly the work done by a virtual displacement does not contain constraint forces. That's how we have been able to eliminate constraint forces. After that, it is just straightforward application of Newton's law and keeping track of the algebra of the generalized coordinates which I have versus R1, R2, Rm required to specify the end point. It's absolutely straightforward after that. But at every stage, the mathematics of it depends on the way I have defined my virtual displacement. There I have written down all the properties of virtual displacement when I discussed example 1. All those properties I will use as you can see here. I think this is all that I wanted to discuss here. There are a few more things which we can talk about. Ignorable coordinates. If this does not depend upon q, then this term is automatically 0. So this gives me constant of motion, any ignorable coordinate. All those will take us into more study of Lagrangian mechanics. I'm sure many of you think. Here I have just explained to you how to derive them so that all the basic concepts there are clear. So let me stop here, and if there are some questions I would like to answer them. Otherwise,